Let's take a look at another type of problem now where we're dealing with charges, 3 charges in fact, but this time not in a row. This time, as you can see in example 10.5 on 534, we have 3 charges, A, B, and C, but those 3 charges are oriented like this. Sphere A, charge of 2.10, negative 2.10 times 10 to the minus 6 coulombs. Sphere B is over here. So sphere A is to the left of sphere B. It's going to be positive 1.50 times 10 to the minus 6 coulombs. And the distance that separates those, 2.0 times 10 to the minus 2 coulombs. Then it tells us charge C is located directly below sphere B. So C is going to be down here. The distance that separates them is 3.00 times 10 to the minus 2 meters. And the value of charge C is going to be positive 1.80 times 10 to the minus 6 coulombs. Sorry, yeah, you're right. Thank you. Does that diagram make sense to everybody? Yes? Shane, you got that written down? Do it. The diagram's, in a sense, the easy part, in a sense, the hard part. Okay, all of you, when we started this question, probably could have drawn that diagram based on the wording that was given to you in that question. But you might not all be able to go to the next step. Having said that, after we go through it, the next step is probably among the easier of the steps, after we've gone through it once. What do you think we're going to do next? After we've got this diagram drawn, what do you think we're going to do? Based on what we've done for the other questions, what are we going to do? Split it up in X and Y, maybe, kinda. Brenda? Yeah, let's figure out the direction of the forces first. Let's get a free body diagram drawn for charge B. And then if we have to deal with X and Y components, we'll deal with that, okay? Charge B has 2 forces acting on it, A on B and the force of C on B. A and B are both oppositely charged, so that means that's going to be an attractive force. If A attracts B, which way is it going to attract it, to the left or right? A and B come together, right? A and B are pulled towards each other. Which way is B going to be pulled as a result of that attraction? Pulled to the left. Let's call it the force of A on B is to the left. A attracts B to the left. Now, A is attracted to the right, but we've said this many times before. We don't really care what happens to A because we're trying to find the net force on B. Now, there's also a force of C on B. That's a repulsive force, right? Because they're both positive. If B and C are repelling each other, then what's going to happen to B as a result of that repulsive force? Ashton? It's going to be pushed upwards, right? So let's draw that upwards. Now, C is going to be pushed downwards, but once again, we don't really care what happens to C because that's not the question. So we've got our free body diagram drawn, the force of A on B, the force of C on B. Let's now, before we worry about any kind of components, Jordan, let's now calculate the values of both of those forces, FAB and FCB. And this is an easy step. Right? This is what you've done 100 times before with the questions that you worked on Thursday, on Friday. FAB is KQA, QB over R squared. Notice we're dropping the sign of the charge again. We always do. Just because it's a 2-dimensional problem here doesn't mean that we don't have to follow the rules that we've always followed. Do the math on that one. I get 70.79625. Anybody else get that value? Good. Let's calculate the force of C on B now. We go through the exact same process to do that. QC, QB over R squared. This time the distance separating them is going to be 3.00 times 10 to the minus 2. And once again, don't forget to square that, the most common mistake that people make on these problems, forgetting to square that distance. I get 26.97 when I do that. Anybody else get that? No? Anybody else get that value? Good. Thank you. All right, now Jordan made a comment early on in this question. Maybe we should do some components, some x and y components here. And that's not a bad thing to be thinking, and not a bad thought to come to the mind when we see a problem like this, because we do have two dimensions here, right? We have a force that's in the x dimension and a force that's in the y dimension. In the end, if we had funny angles for forces, then we've got to start doing components and then add up my x's and add up my y's. But in the end here, we have only one in the x direction and only one in the y direction. We don't have to go through that component process because we've already got our components. Does that make sense? We've already got x and the y component already. The x component is negative 70.79625. The y component is positive 26.97. So now at this point, I'm simply going to redraw this as a vector diagram. This is a free body diagram. We need to redraw it as a vector diagram so that we can get both the magnitude and the direction. If I just joined these two lines together, I would get the magnitude of the force correctly, but I wouldn't get the direction. If I want to find the direction, I've got to redraw it, 70.79625 newtons, 26.97 newtons, and then I've got to draw my resultant vector drawn from start to finish. That resultant vector, that resultant force, at least the magnitude of it, is going to be found by the Pythagorean theorem, which we've done a million times before with conservation of momentum, right? And we've done a million times before in Physics 20. And then we're going to find the angle in the same way as we've always found it with momentum and velocity and displacement in Physics 20. We're going to say theta is equal to the inverse tan function of opposite over adjacent, 26.97 divided by 70.79625. What do we get for the force there? Does anybody have that? We get the force there of 75.8 newtons. That's the magnitude of the force. And the direction of the force is going to be what? 20.9 degrees. In this case, 20.9 degrees north of west. Actually, we shouldn't really say north of west here, right? Because the frame of reference in the question is not north, south, east, west. We just say up from the right or something like that. Okay, does this make sense? Again, the last set of stuff we did on Thursday, the last day that I was here, where we had 3 charges in a row, was really just a combination of what we did this year with Coulomb's law and what we did last year with Newton's law of gravitation when we had three masses in a row, the Earth, the Sun, and the Moon, or whatever, in a row. This is really just another combination of things that we've already done, right? Coulomb's law, free body diagrams, adding up forces when they're in 2 dimensions using the Pythagorean theorem and the inverse tan function. Again, a combination of what we've done this year and a combination of what we've done last year. Okay, what I'd like you to do right now is, of course, after you've got this copied out, is take a look at questions on page 534. All right, question number 2 we'll take a look at here. Calculate the net electrostatic force on charge B shown in the diagram here. So they give us a bit of a break in this question that they give us the diagram. It's not really a huge thing because we could draw the diagram fairly easily in question number 1, but we already got it in question 2, so much the better. We're trying to find the force on charge B. So there's a force of A on B and there's a force of C on B. Tell me, which way does the force of A on B act? Is it, first of all, an attractive force or a repulsive force? A on B. A is negative, B is positive. Do they attract or repel? They attract each other, right? Because opposites attract. If they attract each other, the force of A on B is going to be to the left. B is attracted towards A. Now, A is also attracted towards B, but we don't really care about that because we're not trying to find the force on A. Now, we've also got to find the force of C on B. C is negative, B is positive, attractive or repulsive. This is the easy part of the question, right? Negative and positive is always going to be attractive. So if it's attractive, C is pulling B downwards. It's pulling B towards it, downwards. Now, B is also pulling C which way? There's a one-word correct answer. There's also a two-word answer that I would accept here. The one-word correct answer is, well, B is pulling C upwards. The other answer I would accept is, who cares? Who cares which way C is being pulled? We're not trying to find the force on C. We're trying to find the force on B. Now, we've got the direction of both of those forces. Let's calculate the values of both of those forces now. We've got to be careful with a couple of things here. We've got some different units going on here. Microcoulombs for the charge and centimeters for the distance. Neither one of those units are uncommon for this kind of thing, just because of practical things often end up being microcoulombs or nanocoulombs and centimeters. But we still have to convert it to those base units. Let's get the force of A on B. It's going to be found by saying KQA QB over R squared. That's 8.99 times 10 to the 9 times 2.00 times 10 to the minus 6. Couple of things here. We've got to put the 10 to the minus 6 on there, and we've also got to drop the sign of the charge. Charge B is 1.00 times 10 to the minus 6. We divide that by the distance squared. Centimeters, we're going to remember to convert that to meters here because we circled it in red. 0.010 meters. And don't forget the most common mistake that people make with these problems, don't forget to square the distance. What do we end up getting for the force of A on B? Someone's got to have that by now. What is the value of that? 79.8? 179.8 newtons, thank you. All right, so that's a relatively straightforward part of the question, right? Just calculate the force between two charges, which is exactly what we were doing Wednesday, Thursday of last week. Let's get the force of C on B, which is equally as straightforward. QC is 2 microcoulombs. It's actually minus 2 microcoulombs, but we're going to drop the sign of the charge. And we can't forget the 10 to the minus 6 there. B is 1 microcoulomb. And if we divide that by the distance, that's going to be 0. Hey, these numbers are the same, aren't they? If the numbers are the same, then obviously we're going to end up with the same value of force, 179.8 newtons. Now, so we get the same number for the force of A on B as the force of C on B. That's obviously not going to be the case all the time, right? It doesn't change how we do the question. Now that we've got both forces, now we've got to change that free body diagram into a vector diagram. The vector diagram is always drawn head to tail or front to back. 179.8 newtons to the left, and then we have 179.8 newtons down. The resultant vector, which is really the force that we're looking for here, is the hypotenuse there. And then, of course, the angle is drawn from the start right here. We're going to calculate the force using the Pythagorean theorem. We end up getting 2.54 times 10 to the 2 newtons. When we do the math here on the angle, we're going to use the inverse tan function, or we can just look at it and say if the opposite and adjacent side have the same value, then what are we going to get for the angle? 45 degrees, right? Now, if you labeled it as 45 degrees here, that'd be fine. I'd take that. They've used their notation that we tend not to use. They got 225. Remember where that comes from. This is 0. This is 90. This is 180. Well, 45 degrees past 180, so it would be 225. Right? 45 plus 180. If that notation confuses you a little bit, don't worry about that, okay? Just worry about getting 2.54 times 10 to the 2, and then the angle of 45 degrees. Right? Joel? I'm sorry, say it again. I wouldn't say it's useless, but in this case it's not necessary. Yeah, you're right. We need to put it into 3 digits. 2.54 times 10 to the 2 is in 3 digits. 254 is also 3 digits, right? No, one is not more right than the other. The reason, Joel, that I've put it in scientific notation, I guess out of habit. And the reason it kind of becomes habit is because oftentimes on those numeric response question on exams, we see it in scientific notation. If it doesn't ask for that, don't worry about it. But just be able to put it into scientific notation just in case you see one like that on the exam where it requires you to do that. Right? Okay, here's your homework for tonight. Oh, you thought you got away with it, didn't you? The bell went. He can't assign homework right now. Yes, he can. Page 538. Page 538. Write these down, please. Question 530. Questions on page 538. Question number 1. 2. Braden, you got this? 2. 3. 4. 5. 6. 7. 8, 9, and 10. You got that? Page 538, questions 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right. Have a good night, everyone.